Okay, so slightly different topic, but still talking about pi electrons that are conjugated and structures that have resonance properties. Molecular orbital diagrams. Molecular orbital diagram for what we're doing in this diagram is showing only pi electrons, pi electron diagrams, the pi orbitals. So the molecular orbital diagram for ethene, there's one pi bond and each carbon has a p orbital. So for ethene, we draw two p orbitals because there are two carbons with p orbitals. The bonding molecular orbital for the pi bond is got two parallel p orbitals with the phase matching. So the blue color represents one phase, like a positive phase, and the green color represents another phase, like a negative phase. Okay? Now, in order for a bonding interaction, for a p bonding molecular orbital, the phases must match, and that is the lowest energy orbital when the phases match. And we list orbitals always in order of lowest energy to highest energy. And we always fill orbitals with the electrons at the lowest energy first and then move up. When the phases of the orbitals do not match, we have an anti-bonding interaction. So in order for bonding to occur, the phases must match, and if phases don't match, that's an anti-bonding interaction, which we have called a node. So there's a lot of terminology here. And that's the anti-bonding p molecular orbital. For the total number of orbitals being combined, we should have the total number of combined orbitals that match. So if we put in one p from each carbon, and we have a total of two p's, then the total number of hybrid or orbitals, bonding orbitals that we draw should be 2. So each carbon contributes one p orbital. That makes 2 p orbitals total for ethene, and then we're going to have 2 bonding orbitals total, which is going to consist of 1 bonding and 1 anti-bonding. Okay. Okay, this looks better, right? Starting out, we have butadiene. Butadiene has 4 sp2 carbons, and every sp2 carbon has a p orbital. So that's a total of 4 p orbitals. So we drew the molecular orbitals for ethene. Now we can draw the molecular orbitals for butadiene, knowing that we start with 4 p orbitals. And the lowest energy orbital should have all p orbitals in the phase. So matching in phases. All right. Okay. So the first one that we'll see is, the first one we draw is the lowest energy orbital with all p orbitals matching in phase. And this is called Psi1. And it has 0 nodes. So there are 0 anti-bonding interactions. There are 0 unmatching phases. That's the lowest energy molecular orbital for having 2 pi bonds. All right, then we have the next orbital up, which will have 1 unmatching interaction and 2 matching interactions. So this is still a bonding orbital. We have 2 in phase and 2 in phase and 1 out of phase interaction. So 1 node. Whenever you move to the second tier orbital, there should always be 1 node. The node should increase by 1 for each orbital level that we increase. When we have a total of 4 p orbitals beginning, we should see 4 molecular orbitals from in the way that the orbitals can combine. So this is orbital 2 for butadiene. So then we can move up again in energy, and now we have 2 out of phase interactions, or 2 nodes, as shown by the green lines, and only 1 bonding interaction where the phases match. And that's called Ch3. That's our 3rd molecular orbital for butadiene. Then we have our 4th molecular orbital for butadiene. The last orbital of a molecule, the lowest orbital always has all phases matching. So lowest one, all phases match. The opposite is true of the highest energy orbital. For the highest energy orbital, none of the phases should match. So notice that none of the phases match, and we have a total of 3 nodes. Okay, so we have 3 nodes for the top orbital, and none of the phases match. You can always figure out how many nodes a particular psi level has by starting from psi 1 is at 0. Okay. Now, one of the questions in your homework is going to ask about the symmetry of your molecular orbitals. And so I want to tell you that the odd molecular orbitals are the symmetric molecular orbitals that have an internal mirror plane of symmetry. So if it is an odd number molecular orbital, psi 1 and psi 3, it's going to have the orbital itself will be symmetric with a mirror plane in the orbital. All right, so here's your book's illustration of the butadiene orbitals. They match the orbitals that I drew for you. And as I said, when we draw our molecular orbitals, we're going to fill electrons from the bottom orbital to the top orbital, because we always start with putting electrons in the lowest energy orbital. And you also have to remember that no orbital can hold more than 2 electrons. So in psi 1, we put 2 electrons, and in psi 2, we put 2 electrons, but butadiene has a total of 4 electrons for the p orbitals, the pi bond, pi molecular orbitals. So there's 4 pi electrons, there are not more, and that means that we stop filling because we've reached 4 electrons. So psi 3 and psi 4 are empty orbitals. Now, we have special terminology that you need to learn. The highest energy orbital that has electrons is called the highest occupied molecular orbital, or the HOMO orbital. The lowest energy orbital, which contains 0 electrons, is called the lowest unoccupied molecular orbital, or the LUMO. And this is relevant because this is how our reactions occur. Our nucleophile, the electrons donated by the nucleophile, are in the nucleophile's highest occupied molecular orbital. The electrons accepted by the electrophile from the nucleophile are going to go in to the electrophile's lowest unoccupied molecular orbital. And so these 2 terms are going to come up again in the talk of nucleophilicity and a nucleophile bonding at an electrophile. All right, so drawing for a triene. So say we have a conjugated triene, and drawing the orbitals for that. This is something that you are probably going to have to interpret on exam, our molecular orbitals. So 1, 2, 3, 4, 5, 6, that's 6. So if we have hexatriene, what do the molecular orbitals look like? Well, we have 6 pi electrons, and we have 6 sp2 carbons, so we should have a total of 6 orbitals. How many times? Okay, so 6 sp2, which means 6p, which means 6 pi molecular orbitals. We start at the bottom, all orbitals in phase. Here we have all orbitals in phase. You move up one, and you should have one unmatching or one node. So here's our one node. Okay, then we move up again, and we should have 2 nodes. When you move up again, you should have 3 nodes. Then you should have 4, and then you should have 5. So there should be a total of 6 orbitals in the end. Right. Wait. No. Okay. Okay, so we have our first orbital where all of the orbitals are in phase. All in phase. Then we have one node, so 3 in phase on both sides. Then we alternate 2 in phase, 2 in phase, 2 in phase with nodes between. Then I can show you the other nodes. Let me draw them in. So now we increase by 1 node, so we should have a total of 3. Then we should have a total of 4. And then we should have 5, where nothing matches at the highest energy. Filling in our electrons for each phase, we can label each one Psi1, Psi2, Psi3. Psi4, Psi5, and Psi6. So we should have a total, we have a total of 6 sp2 carbons. We should have a total of 6 pi molecular orbitals. We have a total of 6 pi electrons as well, so we should fill in our orbitals until we've used all 6 electrons. So we fill in Psi1, fill in Psi2, that brings us to 4, and then if you fill in Psi3, that brings you to 6 pi electrons. This ends up with the highest occupied molecular orbital now can be labeled, and lowest unoccupied molecular orbital can be labeled. So the highest occupied molecular orbital is Psi3, and the lowest unoccupied molecular orbital is Psi4. And notice that the odd-numbered orbitals are symmetric. So Psi1 is symmetric. It has an internal mirror plane. Psi3 is symmetric. It has an internal mirror plane. I can fold it in half. And Psi5 is symmetric. All right. Symmetric and antisymmetric orbitals. The odd-numbered orbitals are going to be symmetric, and the even-numbered orbitals will be antisymmetric. So that they're showing an internal mirror plane at the middle of the node, of the 4, at the middle of the molecular orbitals, there should be an internal mirror plane halfway through. Localized electrons versus delocalized electrons. For localized electrons, there is a separation by an sp3 atom between the p orbitals. So the pi electrons are localized. And for delocalized electrons, the pi orbitals are not separated by sp3 hybridized atoms. So again, isolated and conjugated dienes. Isolated dienes are separated by more than one single bond. Conjugated dienes are separated by only one single bond. Now we can cover reactions of isolated dienes, and we're going to use the same reagents that we used with when we studied pi reactivity in chapter 6. So here we have isolated diene reacting with excess HBr. Both of the pi bonds react with the HBr. Bromine is added to the more substituted carbon, and we get this dihalide. The mechanism is the same. The pi electrons add hydrogen and bromide leaves. Then bromide will add to the cation, giving the first halogen added. Then the other pi bond will add a hydrogen. Bromide will leave. Bromide will add to the cation, and we have the dihalide. The mechanism for conjugated double bonds is going to be slightly different. Also, for isolated dienes, you have to consider that the reactivity of the pi bonds is going to be different depending on the stability of the pi bond. So here we have a geminal disubstituted pi bond at the right of the molecule, and a monosubstituted pi bond at the right of the molecule. We know that the geminal disub is more stable, and so should have more reactivity. Thus, the geminal disubstituted bond, if we only have a 1-to-1 ratio of the alkene to the HCl or the halo acid, then the more substituted, more stable pi bond will react to give the major product of the reaction. So the more substituted, more stable pi bond will add H and Cl, and the other pi bond will be unreacted if we have a 1-to-1 ratio. Okay, reactions of conjugated dienes. 1,3-butadiene reacts with Cl2. We know that Cl2 should react with an alkene to produce a dihalide. So if we react this conjugated diene with 1 mole of Cl2, we get 2 major products, both the 1,2 and the 1,4 addition products. And so the 1,2 addition product looks normal. It looks like only one of the pi bonds reacted. And then the 1,4 addition product, you might be thinking, whoa, 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 the pi bond wasn't there. How did the pi bond get there? And that is because of resonance. So if you recall, pi electrons can move. And so if you draw the intermediate of the reaction, then we have the intermediate is Ch2 the halonium ion intermediate, remember, CH, CH double bond CH2. So that's our intermediate. Now our pi electrons can actually move and break the 3-membered ring. So if I move the pi electrons here, moving the pi electrons from between carbons 3 and 4 to between carbons 2 and 3, will cause this bond to break and form a cation, an allylic cation. So this has a resonance structure. CH2, Cl, CH, pi bond, CH, bonded to CH2 with a positive charge. So that is an allylic cation, which we know is at least as stable as a tertiary cation. So we're allowed to have that cation. Then as the second molecule of chloride reacts, the one that's generated when the pi bond adds the first chlorine, it can add to the cation at carbon 1, or it could add to the halonium ion carbon. We could get either reaction, and that's how we produce our two products. So the 1,2 product is when chloride adds and breaks the halonium ring. Breaks halonium ion, and the 1,4 product adds when the pi bond moves, breaks the ring, breaks the halonium, and then chloride adds at the cation carbon. Cationic carbon. So for 1,3-butadiene, we get 1,2 and 1,4 addition products when we react because of the conjugated pi bond being able to move and generate cations and break. For the HBr, this comes from two, this also has two things that occur. So addition of hydrogen creates a cation at carbon 2, and that's an allylic cation. This is the intermediate for the 1,2 product. But we know that an allylic cation has resonance, so I can move these electrons over, draw my resonance structure, positive charge. So notice that the positive charge is either at carbon 2 or the positive charge is at carbon 4. And that explains why we have a 1,2 and a 1,4 addition product. Okay. So 1,2 and 1,4 addition. For a conjugated system of a diene, we will always call whether the diene has 8 carbons total in the molecule, 20 carbons total in the molecule, we will call the pi network carbons 1 through 4 for the diene, okay? So this numbering system has nothing to do with numbering the molecule to name. We are using these numbers to number the pi carbons in the conjugated system. And then we're using those to find those numbers that we add to find the 1,2 and the 1,4 addition products. because we're always going to, for certain alkene reagents, we're always going to form two products. Okay, so for example, for 2,4-hexadiene, we don't number the terminal carbons because we're not worried about them. We're only going to number the pi carbons. And so the first pi carbon is labeled as 1 and the last pi carbon is 4. This produces our two products, with bromine adding to carbons 1 and 2, or bromine adding to carbons 1 and 4. So we have a 1,2 and a 1,4 addition product. When we react with HBr, we know that H adds to the less substituted carbon and bromine adds to the more substituted carbon. So hydrogen adds first at carbon 1, bromine adds to carbon 2, or hydrogen adds first to carbon 1, and then bromine adds to carbon 2. So the two things that add when we use HBr are hydrogen and bromine add. So we get CH3, CH, new H bond at carbon 1, then CHBr, CH, double bond, CH, CH3. And this is the 1,2 addition. And for the 1,4 addition, I'm going to put a hydrogen on carbon 1 of the pi network and a bromine on carbon 4 of the pi network. And that is the 1,4 addition product. So that should clearly explain the 1,2 and the 1,4 addition product and how they come about. We're literally adding our new bonds at carbon 1 and carbon 2, or we're adding our new bonds at carbon 1 and carbon 4. Okay, and we'll look at the book's mechanisms in the next video, and that will give us a second time to review what 1,2 and 1,4 addition look like.